So Wi-Fi came about to solve an interesting problem. Namely, how can we take spectrum that nobody will own and then let wireless devices leverage that unlicensed space? The primary challenge that emerges is how do we provide fair opportunities for access to the channel when there's not a central boss directing access, as happens in the licensed space. Fortunately, the concept of sharing access where there's no central boss is actually not a new concept. So we've had quite a bit of experience with that in the early days of wired networking. Unfortunately, wireless makes this a bit harder because now our nodes are distributed, it takes time to send data to one another, and the communications between them are lostly, in that sometimes data gets lost due to no fault of our own. The question then is, how do we provide access? Wi-Fi adopts what we call a DCF, or a distributed coordination function, to determine who should talk when, for multiple Wi-Fi devices then in the same channel. For now, let's assume that we have 4 devices. We have access point A, and we have devices B, C, and D. For the purposes of channel access, which we are talking about now, everyone operates on equal ground. So we'll assume that everybody should get a fair opportunity. The access point has the same rights to the channel as all of our mobile nodes. The underlying principle for the DCF is something called CSMA-CA, which stands for Carrier Sense Multiple Access and Collision Avoidance. Let's chunk this up to try to understand what's going on. By Carrier Sense, or CS, we mean that every mobile node can sense when the channel is being used. That means we're going to listen first before we as a node are going to try to speak. By multiple access then, we mean that multiple devices then share the same channel. We would like that access to be fair, that everyone has an equal chance to get access over a sufficiently long period of time. By collision avoidance, we mean that we should actively try to avoid collisions. We should be what we call exceptionally polite to others, and by employing something that we call a binary exponential backoff. So let's unpack this and see what it means. We know that the underlying channel is lossy, and that our packets may not always make it to the other side. As such, we expect that packets will be lost. So what we require then is all packets after being sent then require an acknowledgement, or an ACK, in that the other side will say, hey, I got your packet. If we send a packet but we do not receive an acknowledgement, we can assume that the packet was probably lost. We might adapt the rate or the power then to send the packet and increase our chances for delivery. Now, if we're the only one using the channel or sending data, it's not a problem. However, as we noted earlier, Wi-Fi has multiple access. You probably have multiple Wi-Fi accesses at home. That means that occasionally we may talk over each other or interfere with each other, and we need a way to handle that. This happens because our different nodes are distributed, and the wireless signals take time to propagate. That delay means we have to be clever. For Wi-Fi, we try to be exceptionally polite, as we noted just a small bit ago, by employing something called binary exponential backoff. What that means is that in the event of a packet being lost, that may or may not have come from a collision, as we can't tell why we lost a packet, we just know that we lost it, we will then try to roll the dice and wait for the amount of time listed on the dice before we try again. This is also known as the backoff. If we sense the channel, or we fail again, we then double the number of dice we roll, which is where the binary exponential part comes in. The idea is that each dice roll gives me a weight between 0, let's try right again, or the next number, just under the power of 2, where the binary part comes from. In the first round, we could wait between 0 and 1 time slots. In round 2, 0 to 3, in round 3, 0 to 7, and so on. So let's work out an example. Since we are doing a binary exponential backoff, let's assume that we have a dice that can grow in terms of the number of rounds that we've gone through. The number on the dice then tells us how long to wait, or how many seconds before we retry. So let's start off. In the 0th round, we just sense. If the channel is busy, immediately we transmit. Let's suppose that we sense and the channel was busy talking. Let's say node C in this case. Then we're going to roll the dice that has 2 sides, giving us either a 0 or a 1. 1, we sleep for 1, or 0, we try to transmit right away. So let's assume we rolled a 1, but now B is talking. Oh, oops, now we need to back off again. So we're in the first round of back off now, so now we're going to grow exponentially in a binary sense. So now our dice has grown to have the numbers 0 to 3 on it. We roll a 3, and we wait. Wait 3 seconds. Let's sample the channel again. Great, nobody's transmitting. We start, but node C also thought the channel was 3 and started talking at the same time when we collide. Well, let's now pull out our trusty dice again and roll again. Except now we've increased the binary exponent one more, and now we're up to weighting between 0 to 7. We roll a 1, not bad. We wait a second, send our packet, get the ACK, and move on, and our dice reset back down to the original 0th round. The neat math underneath this is that eventually it works out to spread out our communications. Over an infinite window of time, we can show that this is reasonably fair. However, over a short window of time, sometimes you win, sometimes you lose. We call this in networking parlance to be non-deterministic, in that it becomes effectively impossible to know for sure when you'll get service. Over the long haul, this is fair, but who knows how long it will take before it is fair. Wi-Fi does try to cap how big the maximum backoff can be, but even then it doesn't make for a guarantee for service.